In mathematics, abstract spaces can be used to represent all sorts of systems. These are useful to create accurate descriptions of real phenomena, understand its behavior, and even predict or control its evolution. When a single number or variable is enough to represent a system, we can use a point and a line to create a graphical representation. In mathematics, this is called a one-dimensional space or one space, as we can select a value for the number across a single direction or axis. To do this, we first need to define a unit of length. We can establish the relative position from the origin and identify the position of our variable x. Positive values are located to the right of the origin and negative ones to the left. This approach is useful for representing phenomena that require a single number to be described, like the age of a person, the total distance ran by an athlete in a marathon, or the elapsed time since the start of the universe. Each of these phenomena requires a totally different measurement scale, but just needs a single number to be accurately represented. However, if we want to represent systems with more than one variable, we need additional dimensions to represent their values. For instance, if we want to represent two variables, we can create a vertical line to represent simultaneously the value of two variables x and y, obtaining a two-dimensional space or two-space. This is written as a tuple to identify which value is associated with each dimension, and corresponds naturally with a point in a plane. Now, having two variables, we can represent systems like a point in a map or in the surface of a sphere, as only latitude and longitude are needed to point a particular location. We can also represent the height and weight of an individual to calculate the body mass index. Another example would be using these two variables to represent the results of an election with only two candidates. With three variables, we can introduce a third axis and a triple of numbers x, y, and z, corresponding to a point in three-dimensional space. Now we can represent three variables simultaneously, like the position of a particle in three-dimensional space, the state of a thermodynamic system described by temperature, pressure, and volume, or the color of an image pixel using a three-dimensional color space like the RGB representation. Many familiar physical systems contain variables that involve a magnitude and direction, like the forces applied to an object, velocities, and accelerations. Entities having both a magnitude and direction are called vectors, and can be represented by an arrow whose length denotes the magnitude of the vector. For example, in a spring mass system, the position, and the force of the spring, and velocity of the mass are represented by vectors. We can only visualize three dimensions at a time using a coordinate system like the Cartesian coordinate system. But mathematically, there is nothing stopping us from considering additional variables simultaneously in spaces of greater dimension. We can index new variables using the corresponding number of the associated dimension like x1, x2, and x3, and continue using a quadruple adding x4, quintuple adding x5, and so on. In general, we can have n tuples to represent an arbitrary number of dimensions x1, x2, and up to xn, corresponding to a point in an n-dimensional space. As we discussed, using coordinate systems with multiple dimensions, we can describe the position of points and vectors in space, represented algebraically by ordered pairs or n tuples, x, y, and z. Geometrically, we can represent vectors using points in space or arrows that start at the origin and end at the point. Points and vectors in an n-dimensional space have the same properties, and it makes no difference how we decide to visualize them, either using the single point or drawing the segment that joins the point with the origin. One possible way we can visualize a fourth dimension is with the movement of a particle in a three-dimensional space, for which the fourth dimension, corresponding with time, is obtained from a sequence of points in a three-dimensional space represented by a moving point. This approach can help us represent a collection of points on a three-dimensional space, that for each value of time, we have an individual three-dimensional vector. And considering that there is a value of time associated with each point, they correspond with a single point in a four-dimensional space. In the next video, we'll delve deeper into the algebraic and geometric properties of vectors and their fundamental role in mathematical systems. Understanding vectors is not only essential for mastering geometry and linear algebra, but it also has far-reaching implications in fields such as physics, computer graphics, and machine learning. So join us, as we explore the fascinating world of vector spaces, and discover the power they hold, and to understand the world around us.